Okay, got it.
Where is everybody else?
I think Hugh said he was going to log on, so he
Okay.
should be here. Nicole said she might come through.
What? Hugh's not in the academy, keeping company, Charles?
I think I'm not sure where he's at. I think he usually comes around this time-ish, so.
Yeah.
Oh, there he is. Hello, Hugh.
All right, I think we are, okay, yeah, we're all recording, so I'm going to pass the floor to you. Hi, Hua.
Hi, how are you?
I'm hanging in there. So Charles, I'm going to give you the hosting, okay?
Okay. All right. Do you mind just posting the Dropbox, or actually I have the Dropbox link.
I'll do it. Hold on.
Yeah. Oh, thank you. All right. If you guys just click on the link in the chat, that's the Dropbox, and download the contents. We didn't finish last week's notebook, so we'll actually start with that one, and that one is titled Coding Challenge 21122. So we'll finish that one up, and then we'll move on to the next one. So give everyone a minute to get their environment set up, download all the content. Hello, Tom.
Hi, Charles.
Just so you know, we're just gonna, the content for this lecture is in the chat, in the Dropbox link. If you just download those notebooks, we're going to actually continue with last week's notebook. We didn't finish it up, and it's titled Coding Challenge 21122.
Okay, I did the question that you didn't go through last week.
Oh, okay. Well, we're just gonna, I don't know, there's some new people here, so we're just gonna continue where we left off last week.
Sounds good, thank you.
No problem. All right, is everyone set? Everyone's got the notebook open, and we're gonna start. We left off last week on send more money, the send more money problem. So has everyone got the notebook open and looking at the relevant problem?
Yes,
All right, cool.
I do.
I'll share my screen. Just move some of the stuff around, minimize that. All right, so this problem is we want to find a mapping from the letters and send more money to the digits 0 to 9, such that when you replace each letter in send more money with its assigned digit, it meets this constraint such that send plus more equals money. Furthermore, M cannot be 0 and S cannot be 0, because then we don't have a valid number. We have something starting with 0 and we don't want that. So we want to find this mapping such that when we replace the letters with its assigned digit, we have send plus more equals money. And a little hint, you're going to want to look into iter tools, specifically the permutations function. That could help you out a lot, make your code a lot simpler. So are there any questions in the problem statement? All right, so now I'll give us about 15 minutes to sort of think over the problem and write up a solution. And like the function here says, we want to return a dictionary of the mapping from the letters and send more money to the digits 0 to 9. So there's no questions. I'll make a few breakout rooms and we can get thinking about this problem. And like I said, if you've already done this problem, feel free to move on to the next one, or even open up this week's notebook and just start looking at those problems if you are already done this problem. Hey, Sherry, how's it going? Okay. I see you. All right, everyone's back. We're all here. Does anyone want a few more minutes for the problem, or do we want to just sort of review the solution? All right, well, let's go. Does anyone have a solution that they'd like to share? All right, well, we'll just go through my solution. Let me just share my screen and we'll go through this together. Share. Okay. So here's how I approach the problem. So I said, so the first thing we need is we have all these letters in send more money, right? We have duplicates. So really the first thing we want to do is first we want to get a list of all the unique, we want to get a collection of all the unique letters in this string, send more money. So given the 4 primary data structures in Python, which one sort of utilizes this uniqueness property that we want? It's a set. A set can only have unique elements. It can't have any duplicate elements. If you try to add a duplicate element, I believe you get some sort of error raised or it just doesn't pass the element in. So the first thing I said is the letters I'm interested in, it's just going to be equal to set of the string, send more money. All right, what that's going to do is I'll just actually go above and I'll just run something like this. So if I say set of AABB, what that's going to return is just a set of the elements A and B. It gets rid of all the duplicates. All right, so now we have, just delete this. So now that we have this set letters that only has unique letters and send more money, the next thing we want to do is use my hint is we want to generate, the idea is to generate every possible mapping and just test if the mapping works. So I need to generate every permutation of the digits 0 to 9 and map them to send more, to the letters and send more money. So what I'm going to do that is I'm going to say permutations or perms. It's just going to be equal to, I'll have to import iter tools. So I'm going to say from iter tools, import permutations. So I'm going to say perms is going to be equal to permutations of the digits, right? So we want to say range 10. This is just going to give me a list or a generator of the number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So we have our letters and we have all the permutations of the digits. So now what we need to do is we need to brute force, go through every permutation, map that permutation to the letters and see if our mapping satisfies the constraint send plus more equals money. So what I'm going to do is I'm going to say for every permutation in perms, I'm going to define a mapping. I'm going to say my mapping is going to be equal to, well, how am I going to make this mapping? I want to sort of combine together the letters and the perms. So does anyone know a function that sort of puts 2 things together? All right, we're going to use the zip function. So we'll say zip letters, and we're going to zip it with the permutation that we want to use. So now what this returns is actually, I believe, a generator that spits out tuples. It's not exactly we want a dictionary. So what we're going to do is just cast this to a dictionary. It's really easy in Python. We just say dict of this zipped object. So now what that's going to generate is if I just print mapping and then break, just define that below, and I run send more money. What this generates is, so this is one of the permutations, 0, 1, 2, 3, 4, 5, 6. It's actually the first permutation. It's just the list in order. And what I've done is I've mapped the letters and send more money to this to the permutation. So now we have this mapping. So now the next thing we want to do is we want to see if this mapping satisfies the constraint send plus more equals money, right? So what are we going to do? I'm actually going to define a helper function up here. I want to say def word to number. And what this is going to do is going to take a mapping and some word. And what it's going to return is, given the word, we're going to generate the number that that word corresponds to by the rules of our mapping. So I'm going to define a result variable, just going to be an empty string for now. And you'll see why I'm using a string. It's a little hacky, but I think it's like the easiest way to write the code. And what we're going to do is, so for every letter in Word, I am going to append to my result. So I'm going to do a result plus equals mapping of letter. So the only issue here is this mapping of letter is actually an integer. And you know what we could do? We could, for every word for every letter in the word, we can take this element and multiply it by 10 to some power corresponding of where we are in the word and try to like generate the number that way. And that's totally fine. But just for simplicity, I think it's a little bit easier, albeit hackier, to just cast this thing to a string and append it to the result. All right, so we're going to do this for every letter. And then all we want to do at the end is, so now at the end, we have the result is equal to some string, right? So we have like 6. If we want to get the integer of this string, the integer representation of the string, all we do is cast it to a string using the str method. So our last step is I'm going to say, result. It's just going to do a string of result. Oh, sorry, int of result. I'm sorry. Before I said we have a string representation of the number. We want to make an integer representation of the number. So I say int result. My bad. So now this function is going to take some word and it's going to generate the number from that word based on this mapping. So now if we go back to our send more money function, we actually have this mapping now, right? So now what I'm going to say is going to make a variable called send. And what this is going to do is going to say send is going to be equal to word to number of the mapping. We're going to pass in the mapping we just generated, this guy right here. And we're going to pass in the string send. More is going to be equal to what? Does anyone know what we're going to put here? All right, we're going to use our function again. I'm say word to string. We're going to do mapping, passing the mapping we just made, and we're going to find out what the representative of more is here. And now lastly, we're going to say money is going to be equal to same thing, word to string. We'll take this mapping, and we're going to say money. So now what do we want to check? We have the integer representation of send, more, and money. What we want to check now is we want to make sure send plus more equals money. So all we want to say is if send plus more equals money, well, let's just print the mapping. Let's just see what it is. So now here we have everything. We started out, just to reiterate, is we first got all the unique letters from send more money, right? We generated all permutations of the digits. So we can generate every single mapping of the digits to the letters in send more money. And all we're doing is a brute force solution. We're going to look at every single permutation. We're going to make the mapping of the permutation of the letters to the permutation. And we're just going to create the integer representations of the word send, of the word more, and of the word money. And lastly, we just see if send plus more equals money, print mapping. Is there anything I'm missing here? So one of the constraints of the problem was that M can't map to 0 and S can't map to 0. So really what I want to say is over here, this mapping, before I even continue and do anything, I just want to say if mapping of M is equal to 0, or mapping of S is equal to 0, we want to continue. We don't even want to consider this permutation because we know it doesn't satisfy the constraints laid out for us in the problem. All right, so now if we run this or do this, hopefully, word to number, line 3. Oh, whoops, it doesn't like that. I have space there. Fair enough. Okay. And now if we generate this name word to string, word to number, my bad. I typed Let's fix up some typos. All right, we'll run it again. Hopefully we run this. Oh my gosh. Is 7 plus more equals money? Why doesn't it like this? Let me just for the sake of time, I'm not gonna sit here and just going to
You did
this
return
here.
it from word to number.
Oh yeah. I did return. So I have the return statement here now. So now we run it. It's gonna take a little bit because it's gotta go through every single permutation for a 10 element list. There's a decent amount of permutations, so it's gonna take a while. No more than like 20 seconds. So it's thinking, and like I said, this is brute force. So we give it a few more seconds. We actually come out with this mapping. So we find N is 6, R is 8, S is 9, D 7, and so on and so on. And if we actually, did the mapping and plug these numbers in, we'd find that it actually does meet our constraint, and that send plus more does equal money. Are there any questions?
I have a question about the zip that you did. So, since letters, the set letters is shorter than perms, is it just going to match the first 8 characters and then kind of cut off the last 2 digits in perms?
Yeah, exactly. So if zip takes 2 iterables, and what it's going to do is going to zip the iterables together up to the shorter iterable. So if I have L1 is equal to 1, 2, 3, I've got L2 is equal to 1, 2. Then if I do zip is equal to zip L1, L2, and then I want to say for A, B in zipped, print A, B. What it does is it's only zipped up the first 2 elements, since the shortest list is only 2 elements long. So it just totally ignores the third element of L1. And that's why over here we have 2 things printed out. Like they're the exact same thing, but it's because since we have a set of 8 letters and and our digits are 9 elements, we're going to have a single duplicate. Are there any other questions about this problem? All right. If not, we will move on to the next problem. Here we have more of a thought problem. So this is a probability question. So we have Alice and Bob agree to meet in the park. They agree to show up at some random time between 12 p.m. and 1 p.m. They will wait 20 minutes for each other, for the other person, or until 1 o'clock, whichever comes first. And assuming they stick to their word, what is the probability that they will meet? And once you get a solution, if you want to try to extend your solution to any time interval or any waiting duration, feel free to. But for now, just stick with a concrete example of Alice and Bob showing up between 12 and 1. They'll each wait 20 minutes or till the end of the hour, whichever comes first. And what is the probability they meet if they both choose the times to go to the park at random? Any questions about the problem statement? All right, I'll give us another, let's say 15 minutes. So we'll meet back at 10:52. And we will discuss the solution or anyone's a line of thought. And I'll make the breakout rooms now. generalize this. All right, I guess we'll go over the problem now. Does anyone have any thoughts they want to share on the problem, or any solution or partial solution or observations about the problem?
Do you consider, Charles, do you consider the probability of them not meeting first? Or do you consider like the probability of them meeting and then like add up the different scenarios?
I personally just considered the probability of them meeting, but if you find the probability of them not meeting, then I guess it's just 1 minus that. I'm not sure if it's any easier to think about the probability of them not meeting than meeting, but since one is just the inverse or 1 minus the other, I suppose you can consider it either way.
Mm.
So are there any other thoughts or questions about the problem? Okay, so the problem is, you know, Alice and Bob meet between 12 and 1. They're gonna wait 20 minutes for each other. So really the first observation is this problem boils down to whatever time, let's just say, whatever time Alice shows up. Can you guys see that? Is that inverted, or is that inverted, Hugh?
It's not inverted, but it's very hard to see, Charles.
Oh, sorry, here.
So the light is very dim, so we can't see the board. I can't see.
Oh, okay.
You're writing on the board like very clearly. It's
You can't see this at all. You can't see that this is in A.
Kind of, but very small.
Oh, sorry. Let me see if we have a darker marker. That's not any darker.
Or maybe writing it dark, like larger, writing bigger would help.
Okay. Here, let's see. So let's say.
Yeah, this is better.
A.
Thank you. No, I can see it.
Okay.
Yeah, that's
Okay. All right.
yeah.
So really, what we want to consider is what this problem boils down to is whatever time Alice shows up, and whatever time Bob shows up. Really, the problem boils down to we want to make sure they show up within 20 minutes of each other, right? So really what we're looking at, and it doesn't matter if Alice shows up before Bob or Bob shows up before Alice. The only thing that really matters is whether they show up within 20 minutes of each other. So the way we write that mathematically is, well, does anyone know how we would write that mathematically? What we want to say is that whatever time, if A represents the time Alice shows up and B represents the time Bob shows up, then really all we want to say is just we want the absolute value of these times subtracted. So really what this problem boils down to is finding out when does this inequality or when does this situation hold? When is the absolute value of Alice's time minus Bob's time less than or equal to 20? So that's sort of the first observation about the problem, is sort of boiling it down to what is essentially stripping away all like the physical worldly elements of the problem and really boiling it down to this inequality. Is we have two variables, Alice's time, Bob's time, and we just want to find out when is the absolute value of the differences less than or equal to 20, right? So how are we going to figure that out? Well, there's a nice geometric representation of this problem. Is if we just get rid of this. All right, let's just make this square nice and big. All right, so it said between 12 and 1, right? So what I'm going to do is relabel the time between 0 and 60, just 0 to 60 minutes, right? So I'm going to have on this axis, I'm going to have the time Alice shows up. And on this axis, I'm going to have the times that Bob can possibly show up. And here we have, this is the 0th minute of the hour, the 12 o'clock, and here's the 60th minute of the hour, just 1 o'clock. So what this really represents is sort of the sample space of all possibilities, right? Anytime Alice and Bob shows up can be represented by a point in this sample space, right? So this is like, whatever, 20, 40, this point represents Alice shows up at the 20th minute and Bob shows up at the 40th minute, right? So really what we want to find is where in this sample space is our previous inequality hold. Really what we want to find out is where is the absolute value of A minus B less than or equal to 20, right? So let's look at it. Let's say Bob shows up at the 0th minute of the hour. Time frame does Alice have now to show up such that they meet? Alice is only going to have till the 20th minute. So let's label this 20. Right? So if Bob shows up at the 0th minute, Alice has to show up within this time frame here for them to meet. Okay, let me make this 20 a little further over. Okay, now what if Bob shows up, or sorry, yeah, what if Bob shows up at the 1st minute? Then what time window does Alice have to meet Bob? And so what time window, what values for A minus 1 is less than or equal to 20? What values does this inequality hold for A? That's anywhere from 0 to 21, right? So we know that if Alice shows up at 1, Bob shows up at 1, Alice can show up for anywhere from 0 to 21, and we'll know they'll intersect. And if we continue this line of reasoning, what we end up getting is this region. What we find here is this region and this region here. So this is 20, this is 20. This region here is actually the region of the sample space where A minus B, the absolute value of A minus B is less than or equal to 20. Any point in here, any x, y, when you plug them into this equation, they're going to satisfy this inequality. So we found this region of the sample space such that this inequality always holds in this region. Up here is the point 40, and here is the point 40. This is the point 20, and this is the point 20, right? So if Alice shows up at the 60th minute, that means Bob only has 20 minutes to meet that time. That's represented here. And we see this, so this region represents the inequality, the subspace of the sample space that satisfies this inequality. Are there any questions about that? So now we know where this inequality is held. So now how do we find the probability of this inequality holding, given any random A and random B? We just want to divide the areas, right? So we want to find this area, this whole area here, where the inequality holds, and just divide it by the whole area of the sample space. So what's the area of the sample space?
3,600. Right?
Yeah, exactly. 60 squared, right? Hello, Nicole. Right, so that's the area of the whole sample space. Now, what's the area of just this region? Remember, this is point 20. Sorry if you can't see, but down here is 20, 20, and this point up here is a 40, and over here we have 40. So the area of this region is really the area of the whole thing minus the area of these two triangles, right? That's how we can isolate this area. So it's really just, if we move over here, we get, it's 60 squared, 3,600, like Sherry said, just for the sake of space, I'll just say this, minus the area of these two triangles, right? So the area of triangle is 1/2 base times height. We know the base 40, height is 40, and it's the same thing for this triangle over here. This is length 40, and this is length 40. So we know that the area of each individual triangle is 1/2 40 squared. So when we add the two areas, we get 2 times 1/2 40 squared. So it's just 60 squared minus 2/2 times 40 squared, which is just 40 squared. And this is our answer. This is the probability that Alice and Bob meets. This is the probability that given two random variables, A and B, constrained to this sample space, the probability, the absolute value of their values is less than or equal to 20. So this general strategy is like, I think it's really, really nice to draw up a sample space and then just find out, boil the problem down to the inequality you need to find that holds, and then just find the region of the sample space where that holds and divide by the whole sample space. What's nice about this problem is potentially some of your approaches you may have implicitly assumed time is discrete. You may have said, well, let me break it up by minute case, but nowhere in the problem did I state that they had to meet on the minute by the minute. So you're sort of like implicitly introducing this like discreteness that was never actually introduced in the problem at all. What this is nice about here is there's no sort of implicit like expectation of discreteness. Everything is continuous. A is a continuous variable, B is a continuous variable. Nowhere do we muddy the waters with this like sort of assumption of discreteness. So I think it's a really nice geometric solution. Always, if you can like try to draw out the sample space, it's always like a good first step to sort of getting some intuition about the problem. Are there any questions about this? All right. Well, that being said, let's generalize it. So I'm going to have the same sample space. So the generalized problem is just Alice and Bob are given a time window from time, whatever time t1 to time t2. You can just say time 0 to t, right? They're given some time window and they're given some waiting window that's less than the time window. You want to find the probability that they meet. So before our waiting window was 20 and our time interval was 60. So now it's your time window is just t and your waiting window is w. How do you generalize this problem? All right, well, first let's look at the axis. So first we have Alice's, the possibility that Alice can take and the possible times Bob can show up, right? And our value over here is we said, well, some time window, right? So let's take the 0th time element of that window and we'll call this over here t is the last time element of the window. So it can be, 12 to 2, 12 to 3, 12:43 and 23 nanoseconds to 2:42 and 19 milliseconds. Doesn't matter. We have generalized it from saying 0 to t. Now it's gonna be the same thing over here. Bob has the same choice of showing up as any time between the 0th time element and the tth time element. All right. So now, now we have to incorporate the waiting window. So remember, what we're trying to solve is the same thing. We want to say the absolute value of A minus B is less than or equal to the waiting window. We'll call that W. So it's the same argument before. If Alice shows up at, well, let's say if Bob shows up at time 0, well, then Alice can show up anywhere from the 0 up to W, right? And now if Alice shows up the time window, well, then Bob, for them to meet, can show up anywhere between the 0th to W time element, right? And then we have the same argument before, is that we find that if we sort of work this out step by step, we find that the area where this inequality, A minus B less than or equal to W holds, is the same geometric shape as we had before, right? Where this value is W and this value is W. Oh, sorry, this value is T minus W and this value is T minus W. Right? So does anyone want to take it home and show me the generalized solution, algebraic solution to this problem? All right, well, it's the area that, remember, so the first thing we did was divide by the area of the whole solution space, which is just t squared, right? And then we wanted to find the area where the inequality holds, which is just this region over here. And the way we did that before was we got the area of the whole space and subtracted off the triangle areas. So we get the area of the whole space is again just t squared minus, well, this length here is just, if this is point t minus w, well, then this length is just t minus w, right? And this length is also t minus w. So we get minus t minus w squared, since we have the area of this triangle is t minus w squared over 2. The area of this triangle is t minus w squared over 2. We add them, we get the total area is t minus w squared. So in general, given some time window, t, and given some waiting period, w, the probability of 2 people meeting, given that they pick a random time in that time window, is this, expression over here. T squared minus t minus w squared, all divided by t squared, where again, t is the time window and w is the waiting period. Are there any questions about that? Hello, Hadar. Okay, if there's no questions, then I think now's a good time to take I think we'll just take a 5-minute break, let everyone catch their breath, get some water, go to the bathroom, do whatever. And we'll meet back at 11:12, where we will start off with this week's coding problems. All right, everyone in 5 minutes. All right, so we're gonna continue on with the notebook as I meant for this week. So if you go back, and I will repost the Dropbox link just in case anyone can't see it in the chat for anyone just joining. 1 second. We're gonna be working with the notebook titled, Coding Challenge 21522. Sort of, we're going to do some recursion work, and we're going to talk about sort of how to optimize recursive functions. So let me just share my screen. So we're going to work through these 3, or there should be 4. We're going to work through these recursion examples. So the first one we want to work on is this Fibonacci one. We just want a function to compute the nth Fibonacci number. And for anyone who's not familiar with the Fibonacci sequence, it starts out with seed values 0, 1. And then for the nth element in the sequence is determined by adding up the prior two. So Fibonacci of n is equal to Fibonacci of n minus 1 plus Fibonacci of n minus 2. So we get, the next element will be 1, then we get 2, then we get 3, and we get 5, 8, and so on and so on and so on and so on. So the first function, fib recursive, is I want you guys to compute the nth Fibonacci number using recursion. And I guess I'll give you guys about, we'll do till 11:20, 7 minutes to work through this one. So yeah, just compute the nth Fibonacci number using recursion, and we're going to come back and talk about pinwheel solutions and sort of discuss where optimizations can be made when you are defining functions like this recursively. I'll make the breakout rooms, and if anyone has any questions, I'll be here to answer them. All right, I think we're gonna come back and talk about the solution. Does anyone have a solution, a partial solution? Any thoughts on the problem? All right, well, we'll just run through it pretty quickly. A lot of us probably have seen this. It's sort of like the quintessential recursion problem people will first see. This in factorial. So with recursion, as always, the first thing we can think about is sort of our base case. Is if we're going to recursively call Fibonacci, then when do we want to terminate for the Fibonacci recursion? When do we want to return a value? What are our base cases, our seed values?
So if n is 0 and if n is 1 or 2.
Yeah, well, if n is 0 or 1, because I gave you the seed value or 0 and 1. People sometimes define the seed values differently. Sometimes they say 0 and 1 are the seed values, or 1 and 2. But for this example, it's 0 and 1. So exactly. So what we want to say is if n, we can say after this, we do a little tricky. If n is less than or equal to 1, we're going to return n. So what this is going to do is if we get to n equals 1, then we return n. Actually, we just, yeah, if n equals 1, we return n. It's never going to get to 0 because it's always going to hit 1 before 0. So really, this is redundant. We don't need to say this. We just say equals. We're going to return n. So what actually is something that an issue is here? Given you give this function to a user, how can they break it?
If they put
They can give a
0.
value. Oh, yeah, exactly. Give a value like 0. So it's not necessary, but we just do a decent like check. We just say, if n is less than 0, we can just throw an exception. We'll just raise exception. Nice try. No. You can be more meaningful with your exception messages or whatever, but for this case, we know what we mean. Okay, so we have a base case, right? So how do we get to the base case? What's the recursive equation that we want to write next? Given fib, oh, you guys can't see that, it's so light, sorry. Given fib of n, how do we compute fib of n?
N minus 1 plus n minus 2.
Yeah, we want to say fib of n minus 1 plus fib of n minus 2, right? Because the nth Fibonacci number is just the sum of the previous two. So it's really just f n minus 1 plus f of n minus 2. So we're going to write that in code. It's very straightforward, same thing as always. Otherwise, so if n equals 1, we're going to return n. And we'll say else, we're going to say return fib, fib recursive is the name of this function. Fib recursive of n minus 1 plus fib recursive of n minus 2. All right, and this should be good. So we run this. This should work. If we just go do recursive 3. Oh, what's the issue? What's the issue? What's the issue? What's the issue? Let's just do this. Okay, so fib recursive 3 returns 2. That's right. That's the third element, 0, 1. Ooh, this is actually the fourth one. That's fine. We just say n minus 2, n minus 3. We'll just leave it as is. All right, so this function actually computes the fourth Fibonacci. That's fine. 0, 0, 1. Oh, the third is 2. 0, 1, 2. Okay, so something that's an issue with recursive calls is a lot of times there's repeated work. So if we draw out the tree of the recursive calls, sort of what happens when I want to compute f of n, what gets called? F of n minus 1 gets called. Let's just do a concrete example. Let's do f of 6. So f of 5, this calls f of 5, and this calls f of 4, right? But then what is f of 5 call? F of 5 calls f of 4 and calls f of 3. And what does f of 4 call? F of 4 calls f of 3 and f of 2. Can anyone see an issue or see where we're doing repeated work just based off this partial tree diagram of the recursive call? The issue is we're doing a lot of repeated work. We can see here. So in this layer, we can see that we're computing f of, so over here, so we call f of 6, then we call f of 5, we call f of 4, and f of 4 calls 2, calls 1, so on. But whenever we get f of 4, we've done a decent amount of work just compute f of 4. And the issue is, okay, we've done all the work to compute f of 4 over here on this side, but now we're gonna do the exact same work over here again. So we're doing like double work. And when this tree is massive, you're doing a lot of repeated work. This is just a small example. We already see a lot of repeated work already. We have another one right here. F of 3 is being computed here, but then we need to recompute it over here again. So it'd be nice if there was a way for us to, this repeated work really adds a lot of runtime. So it'd be nice if there was a way for us to sort of save the values. And we can say in our function, like, oh, we compute f of 4 and we save the value. So if any other time in our recursive call, we run into f of 4 again, we don't need to compute it. We can just look up the value and return it. And that eliminates a lot of redundant work. And will make our function run a lot faster. So the example here is, I want to show you, like our recursive call works fine, sort of around 30, it's fine, takes a decent amount of time. 31, it's fine. Go to 34. Still fine. Okay, we'll go to 40. All right, now it's starting to take a decent amount of time. It's taking a long time actually, because like I said before, with f of 40, this tree is massive, and a lot of the value being repeated twice. So what I really want to show you guys real quickly is this method called Memoization, but it literally you just store values that you computed so that you can reference them later. So you don't need to recompute those values and do the whole recursive call. So the way memoization works, what we do is we create this structure that's going to store all of our Fibonacci numbers. So make this thing called memo. And I'm just going to say memo is going to be equal to negative, I'm going to say -1, and I'll explain that in a second, times, let's do this, n plus 1. So what this is doing is going to create an array of length n plus 1. And it's going to initialize every element with a -1. And the reason we do -1 is this is going to tell us later on. We can say we'll know if we've seen this call before, if the value, we'll know we've seen the kth Fibonacci number if memo of k is not -1. We're going to update these values, and every value is updated once we refer back to it. If this value is not -1, meaning it's been updated, meaning we've computed this value before, we're just going to return the value in the memo. We're not going to continue on with recursive call. We're just going to return right there. All right. So with memoization, we want to set some seed values. We want to say we know memo of 0, the 0th Fibonacci is 0. We know memo of 1, the first Fibonacci number, the second Fibonacci number is 1, right? Now what we're going to do is, maybe you guys haven't seen it before, but in Python you can define helper functions within a function. So what I'm going to define is this fib that's actually going to do the work for us. It's going to just take the same argument n. But what's nice is that this Fibonacci argument can now reference this memo that we defined over here. This thing is going to store all the values we've seen before. So let's run through the Fibonacci function again. It's going to be a little different. Instead, now our base case is a little different. We're going to say if memo of n is not equal to -1. What this is saying is if we have computed this value before, then what do we want to do? We've gone through this recursive call. Let's say we're at let's say we computed f of 4 over here, and now we're over here. We hit f of 4 again. What do we want to do? Do we want to run through the whole recursive call, computing everything again, or do we want to reference something?
You want to reference the the first memo.
Exactly. We want to reference, so the nth Fibonacci number, if it's been computed, is going to be stored in the nth element of the array. So we're going to say if memo of n is not equal to -1, meaning we've seen it, then we're going to return memo of n. Right. So if we think about just the base case, so once we hit, the reason we put these seed values is this is our base case essentially encoded into the memo, is once we hit memo of 0, well, it's not -1. So we're going to see it and we're going to return 0. Or once we hit memo of 1, we know it's not -1. So it's going to return whatever value is here. All right. So this is saying if we've seen this value before, if we've computed this value before, we're just going to return the value that we stored in our memo. We're going to say else we haven't seen this value. So if we haven't seen this value, what we want to do is we want to store it in the memo. So how do we say that? If we haven't seen this value, memo of n at this point is actually equal to -1, but what do we want to reassign it to?
Charles, can I ask you a quick question before we move further? So
Sure, sure.
I'm not sure how like the -1 times n+1 comes from for.
Oh, sorry, sure. So this is like a Python way of saying, I want to make an array. Here, let me just go below. I want to say I'm going to create an array of whatever with I want to make an array of all values of 1. And what length do I want to make it? I want to make it length n. Length 4. All this is doing is creating an array. It's going to make every element 1 of length 4. It's like a nice little syntax sugar.
Okay.
I could also say I want my array to just be equal to 1 for I in range 4. That'll do the same thing. If I return array now, that'll do the same thing. This is just like a nice sort of like concise way of writing it out.
Gotcha.
But it's entirely equivalent to just doing it this way or any other way. It's just like a nice concise way.
Okay.
That makes sense to everyone? All right. So memo of n. So right now we're at fib n. We've already determined that this value has not been computed before, right? Because if it has, we would have returned here. So now we're over here. We know the value has not been computed. So how do we compute the nth Fibonacci number? That's what we want stored in memo of n, right? So what do we want to say? How do we compute this Fibonacci number? What we're going to say is, we'll say memo of n is just going to be equal to fib, like we said before, Fibonacci of n minus 1 plus fib of n minus 2. Right? So now we've computed this value and we've stored it in memo. So now what do we want to return from this function? We want to return what we just computed, right? We've just computed the nth Fibonacci number. So now we're going to return what we just computed so that the call before it can use that value, just like in regular recursion. So it's going to return memo of n. All right, any questions right now? Okay, so this is the whole Fibonacci function right here. We didn't include the, we can do like, the if n is less than 0 exception handling, but let's assume we're using this non-maliciously. We're not trying to break it. We know how to compute what Fibonacci's are, what seed values are valid. The last thing to do here is this fib function is defined within this bigger fib memo function. So all I got to do is I just want to return fib of n. Right. So what's happening here, I'll just move all this down here just so it's clear, is we're making our memo, and then we're just going to call this function fib that's going to utilize this memo. This function fib is defined right here, and it's just like our other Fibonacci, except now we're using memoization. We're storing these values so that we don't need to recompute it. All right. So now if I run that, hopefully I go down here to remember. So our time, let's see what 34. Let's try 37. Okay, that's taking a decent amount of time. But now we try fib memo. I think that's what it's called, right? Yeah, fib memo. Oh, did we do something wrong? Why did that take so long? Hold up. Make sure I did everything right. Yeah, I believe everything's right. This should be fib memo. Okay, so now it computes it automatically. So fib memo 37 is computed automatically. Remember, we just did regular fib. Fib recursive was it was called? Yeah. It's going to take its time. It takes a bit longer. And even if we make this like value 40, it's just not going to run in a decent amount of time. This is just not fast enough. But if we run fib mem, what is it called? Fib memo. Oh, I gotta stop it. And we run it, it runs instantaneously. And it's because, like I said, we saved a lot of this duplicate work by storing values of Fibonacci we've computed, so we don't recompute them. Are there any questions on memoization? This is a really popular technique, and in general, recursive problems, the way you would solve them is the inefficient way is to solve it with recursion and no memoization. So you sort of get your grasp on the problem with just solving it sort of recursively as we did before. Just like plain old recursion, no memoization. And the next thing is, well, let's try to avoid duplicate work. So we do recursion with memoization, where we just did that down here. We make this sort of memo where we store values that we've already computed, and we can pull those values if we already computed them, saving us from doing duplicate work. The next step usually is we've done this recursion. Now we want to try and do a bottom-up approach. What this means is we're going to try and do it iteratively. So while we saved a lot of time by memoizing, the memory complexity of this is still, it is still at worst case ON, because the recursion stack is going to be at worst for its first call. It's got to go all the way down to fib of 0. So if you have fib of n and your recursion stack is going to be n elements big, so you still have memory complexity of ON. And this next function here is we want to use, this is a step into the final way we're going to do this. We want to compute the nth Fibonacci using memoization and iteration. So what we want to do is we're going to use this memo, but instead of doing it recursively, we're going to do this iteratively. And the reason it's called bottom up is because instead of starting like in recursion, where we start at the nth guy, and we break the problem down into its components when we eventually reach fib of 1 and 0. Bottom up, you start at fib of 0 and fib of 1, and you build the solution up, and you return the final result. So recursion's bottom down because you're starting at the top and going down. And this iterative approach is you're starting from the base case of the problem and building the solution up from the base case. So that's why it's called bottom up. So what we're going to do now is we're going to implement this bottom up solution. Try thinking about how to do Fibonacci. You can use extra space. Feel free to use extra space. The next step we're going to do with minimal extra space. But try to implement this Fibonacci bottom up using iteration and memoization. And I'll give everyone about, we'll meet back at 11:50 to discuss the problem and anyone's solutions. Excuse me. Are there any questions?
All good?
All right, I'll make the breakout rooms, and if anyone has any questions, just speak up. Jeez. Is that what I look like? Oh no. All right. Does anyone have any thoughts on the problem, or want to share a solution or a partial solution, or any insight they had?
If no one else wants to, I'd be happy to share like kind of what I started drawing up, but it might be totally wrong. So, or like it might not even be close. So I don't know.
That's fine. If you want to share it, you can share it.
Okay. I kind of.
You want to share your
started-
screen,
Sure.
or do you want? Okay.
Okay, cool. So I have like a million tabs open, but it's fine.
That's fine.
So yeah, so like I wasn't sure if we were supposed to just the definition. From the number.
I can't hear you.
Oh, can you hear me now?
Oh, now I can hear you. Yeah.
Oh, awesome. Okay, sorry, I had muted myself. Yeah, so like I wasn't sure if we were supposed to keep this definition of the fib right here, but I just kind of started writing this for loop where memo.
Okay.
So I think that's gonna be totally confused. I'm not sure, but
No, you're on the right track. The only thing is we don't want to use this fib function here.
Okay.
That's not going to do anything for you. But you're on the right track of like, do we have this? We want to do it iteratively, right? So we can use a while loop or a for loop, and it's not quite there, but you have the right idea. Like we want to iterate through this for loop, and we want to assign the kth element in memo equal to the memo k minus 1 element plus the memo k minus 2 element, and then increment k to go on. So I think I'll walk us through my code, and if you want to follow along, you can just like adjust your code on the fly if that works for you.
for sure.
All right. So bottom up. All right. So first thing we can do is, for clarity, we'll make our memo, where we make our structure where we store all the values that we computed, right? So I'm going to do a similar trick to before. I'm going to say my memo just going to be equal to, I'll just say 0 times, and I'll just do this n plus 1. So this makes a n plus 1 element memo that we can store our elements in. And again, I'll make the seed values. So memo of 0 is already 0 because we've initiated everything in our array to be 0. So all I need to do is set memo of 1. I'll just say memo of 1 is equal to, well, the memo of 1 is really the second Fibonacci number, which is just 1. So those are our seed values. And now what I want to say is I'm going to say this. I'm going to say for blank in range. Well, actually, I'll start off with saying this. I'll say for I in range. Where do you want to start computing values? What index do I want to put in for the first index? And where do I want to go to? Our first index is actually going to be 2, right? Because we've already computed the 0th Fibonacci number and the first Fibonacci number. They've already been stored here. So we don't want to write over those values. We want to start really at index 2. That's where our computation is going to start. And we want to go all the way to the end, right? All right. So just like before, we want to put the kth Fibonacci number in the kth spot of the memo. So we're going to say memo of I is really just going to be equal to memo of I minus 1 plus memo of I minus 2. And what this is doing is really, so let's say we want to compute the 5th Fibonacci number. I'll just draw out what this code is doing real quick. Right, we've made our array. It's gonna be size 2, 3, 4. Right, we made our array of size 6. We want to compute the 5th Fibonacci number. So we make an n+1 size array. And we put 0 and 1 as the seed values, right? So now we say for I in range 2 to n+1. So we're going to start here. We're saying memo of I is going to be equal to memo of I minus 1 plus memo of I minus 2. So that's just 1, right? Now, before it was completed, so we go to the next element. So now k equals 3. So that means that memo of 3 is going to be equal to memo of 2 plus memo of 1, right? That just puts 2 in. All right, we finished. Now we go on to the 4th, and we're going to say memo of 4 is really just going to be equal to memo of 3 plus memo of 2. So that's just going to be 3. And now for the final element, it's just memo of 5 is going to be equal to memo of 4 plus memo of 3. And that's just going to be equal to 5. So that's what this code is doing. It's bottom up because, like I said before, we're starting at the base case and we're building the problem up from the base case. Instead of in the recursive case, where we start at the full problem and we break it down. So that's why it's called top down, and bottom up is because we start at the base and we build the problem up from the base. So we've built up our array. We have all the values stored. So now the nth Fibonacci number is stored at the end of the array, right? So we can just return memo of -1. It's just a little nice Pythonic way of getting the last element. And that's it. Are there any questions on this? This should work. Oh, as long as I put the syntax in correctly. Okay, there we go. Now fib bottom up, so I didn't do anything wrong. All right, it seems to work. We compute the 40th, and again, it computes it really quickly because we don't even have a recursive call here. We don't have to worry about anything about doing duplicate work. We really just start from the base case and build up from the base case. So we know we're never going to repeat any work because we're never going back to cases we've considered before. We're always only moving forward. So like before, we've never had to revisit these indices again because the kth Fibonacci number only depends on the prior 2 numbers. So we're never doing duplicate work. Any questions on that? Okay, so there's one thing wrong with this problem is I'll actually quickly go through this. There's one way to increase it is like, so we're using the space complexity is ON here because to compute the nth Fibonacci number, we're creating an array of size n. But like I said before, the kth Fibonacci number actually only depends on the prior 2 elements. So we don't need to store every element to make the kth Fibonacci number. We only need to store the prior 2 elements. And I'll show you how we can code that up real quick. So this is, we'll call this def fib. Let's call it fib final. It's our final form of fib. And what it's going to do, we'll call it fib less memory, so it's a little bit more meaningful. All right, and what we're going to do is we're going to start by setting our seed values. So we're going to say a variable called f of 0 is going to be equal to 0. And we're going to say f of 1, the 1th Fibonacci number, is equal to 1. Right? And now we're going to say, I'm using a little trick. I'm going to say the next Fibonacci number, to define here, you may not need to, but I'll say fib next is just going to be equal to 1. That's the third Fibonacci number, right? So now here's what I'm going to do. I'm going to say for I in range. Again, I have already computed the first 2. I've said the first 2. So I'm going to start from 2 again. Oh wait, no. I want to start from the 0, but I only want to go up to n minus 2. And that's because I want to compute the nth Fibonacci number, but I've already computed the first 2 here. So we only want to do this up to range n minus 2. Because if I did it up to range n, well, I've computed the first 2 already. So if I did it to range n, I'm really actually going to return the n plus 2 Fibonacci number. So we're going to say is for I in range n minus 2, I'm just going to say, well, we want to reassign what f next is. We're going to say f next is equal to what? What is the next Fibonacci equal to? Imagine here we still have just f of 0 is equal to 0 and f of 1 is equal to 1. What is f next equal to? what variables do I put here? Oh, can you guys see that? There we go. What variables do I put here? It's just going to be equal to F. Oh, sorry.
Adding the last two.
Exactly. So it's going to be F0 plus F1. Now what we want to do is we want to update our variables, right? So now what we have is F0 equal to 0, F1 is equal to 1, and we have F next is equal to 1. So now what we want to do is we want to have F next, which is really just F2, is equal to 1. So what we want to do is we want to update F0 and F1 so that next time around in the next iteration of the loop, we can compute the next Fibonacci number. So how would we reassign these variables?
Would you do like F0 equals F1?
Yeah, but we want to do it in a bit trickier. The ordering is a little important. So yeah, it's F0 equals F1, and what would F1 equal?
F next. Oh, so you
Exactly.
need to like update it like okay. So F1
Like from the top
equal
down,
F0.
right? Because if you don't,
yeah.
So you want to say F1 equals F next, and then we're going to say F0 is equal to F1. You see, and everyone sees the issue. If we reverse this, then we're going to mess up our code. It's not going to compute what we want to. We want to first reassign F1 and then reassign F0, because if we reverse it, then it's just going to totally break the code. So it's not going to actually assign what we want to assign to. All right. So what is this? That's essentially it. So now all we return is F next. Right. So we've assigned we've put in our base conditions. We've just assigned this variable could literally be anything. It can be whatever. I just need to initiate it so that it exists in memory so that when I call it, I don't get an error, right? This could have been like, it doesn't matter, -2. Doesn't matter what this is. What was important is that this loop is all I say is that the F next is really just going to be equal to the prior two Fibonacci numbers. And now then we just update the prior two Fibonacci numbers to include, we compute Fn. So now we want to make F1 point to Fn and F0 point to Fn -1. So the next time around the loop, we can just add those two values. And we keep on updating and daisy chaining the values through until we get to n-2, and then we just return the final form of F next, or the final value of F next. So we've avoided using an n length array in memory. We've reduced it to just using 3 variables to sort of store all the relevant information. So we reduced the memory complexity from O of n down to O of 1, because we're only using constant space. It's just 3 variables, which is just O of 1. Are there any questions on that? This code makes sense to everyone?
Yeah, I was wondering, is the definition of memoization like having that array of having that array? So like this isn't,
Yeah, so
fibless memory isn't memoization technically.
no, it's not. Yeah,
Iteration.
technically, no. Like, I mean, it's like sort of splitting hairs. It's like we're not explicitly storing a we're not using like this big structure to store all the information. We're only storing the relevant information. So I think it really depends who you talk to, because technically we're storing values, we're just not storing all the values. We're only storing the values necessary for the computation, right? Because the issue before was with the bottom up where we had this memo. Wait, where's my mouse? Over here, you know, we stored everything, but we didn't need everything to compute the kth Fibonacci number. We only needed fib k -1 and fib k -2. But I mean, I'm not sure if you would call this memoization or not, but I guess the technical definition of memoization is using extraneous or using extra space to store already computed values. So this could technically be called memoization. But in general, you'll see memoization is like you store like this massive array or something like that. Yeah.
Okay, cool.
Yeah.
Thanks for,
So in general, so I want to say how we started was we just had plain old recursion Fibonacci, where we started from the top and we worked our way down. And the issue with that was we saw that there was a lot of computed work. And we saw that we tried to compute anything greater than like fib of 32, it started to take a really long time. So we fixed that issue by memoizing with an O of n array and storing values that we had already seen, so that we don't need to do any repeated work. And that made it run really quickly. But the issue with that memoize thing is we're still using a lot of extra space. on the recursion stack and on the memory or the memo array. So then we went down to bottom up, where we avoided the recursion stack by doing it iteratively. So we only had a memo array of size n. And then from there, we realized that we don't need to store every value. We just need to store the last 2 Fibonacci values. So our final form, fib less memory, is the most optimal form of Fibonacci, where we only use 3 variables to store the relevant information. We do it iteratively, so we avoid the recursion stack, and we do it in linear time. So the time complexity is O(n) still, and the space complexity is O(1). And next week, we didn't have time this week, but we'll just continue on next week. We're gonna actually redo this whole process where we start from the recursion memoization, bottom up memoization, to bottom up with only the necessary information, with a different problem to sort of reiterate the process and just solidify this thought process. Any questions? All right, if there are no questions, I will see everyone next week, hopefully. Take care. Feel free to go through the rest of the notebook on your own if you'd like, but we will pick up next week where we left off this week. Take care. Corey, anything to say? All right. Well, with that being said, take care, everyone. Have a good week.